Sí. Pero es que yo no, ¿entendés que no?
Por
Yo no hice nada. Se hace sol.
Aguantame que me fijo si estamos en YouTube, creo que sí.
Pero es que yo no, ¿entendés que no? Yo no hice nada. Tenés que mutear el YouTube. Se hace sol.
Okay. We are online. Yes.
Tenés que mutear el YouTube. ¿Me escuchás? Hola, hola.
We are online. Yes.
Tenés que mutear el YouTube.
Please, cierren el YouTube, Fede y Sebastián.
¿Me escuchás? Yo no lo tengo abierto. Hola, hola.
Está bien,
Hola,
ahora
hola.
está bien. Ahora está bien. We are online. Sebastián.
Tenés que mutear el YouTube.
Please, cierren el YouTube.
Perhaps, Carol,
No lo tengo.
is it possible that your YouTube is open?
Hola, hola.
Está bien, ahora
The
está bien.
YouTube transmission?
We are online. Sebastián.
Tenés que mutear el YouTube.
Perhaps we have to mute some participants.
What should I do?
Carol, no lo tengo.
Is it possible that your YouTube is open? Do you hear that sound that is going? So someone has its YouTube open. Okay, Martinetto muted and it went. Okay, it was Martincito. Okay, okay, perfect. We are ready. So if you guys tell me, I start. Yeah, we are going live. Bueno, empiezo, Martín,
Okay, it was Martin. Okay. Okay, perfect. we are ready.
Okay, hay que mutear a Martín. So, welcome everyone to this third day of the conference on quantum foundations. We are really glad to have again Professor Karol Zikowski from the Jagiellonian University from Krakow, Poland. He will speak about 36 entangled officers of Euler, quantum solutions of a classically non-solvable problem. Please, Karol, go on.
Yes, thank you very much. Muchas gracias por la invitación a Argentina. I'm only, I regret I cannot come on site to visit Cordoba or Buenos Aires, but I'm very, very pleased to be here with you online, especially that maybe some of you know, we have now a guest from Argentina. So Diego Busanti is here with us, and we have a collaboration on some projects related to quantum theory. But now I will tell you about some other projects which was done together in a collaboration with India. Let me mention Arul Lakshminarayan from Chennai and his student Suhail Later, and my students Adam Burchardt, Wojciech Bruzda, and Grzegorz Reichel-Miercic. Well, let me start a very general question. What is at the center of theoretical physics in general? Well, we would like to answer some basic questions like what is the correct theory to describe the world around us? What is the correct theory to describe the world at the microscale? Is quantum theory, we know, capable to describe the world at the microscale? If not, perhaps we need some more generalized quantum theory. If yes, how such a theory might look like. If no, how to extract as much as possible from the standard quantum theory. Well, some time ago, I was interested in those generalized quantum theories. I published a paper on generalized quartic quantum theory, quartic because instead of density matrices, we use density tensors. But today, I'm going back to the standard quantum theory, and in the framework of standard quantum mechanics, I'm going to look for extremal quantum states and try to find their applications. Well, what about quantum states? I'm pretty sure you know very well what is this about, but let me make a very short introduction. So we consider finite dimensional Hilbert space like n-dimensional Hilbert space. If n is 2, we have a qubit, so quantum bit. So any point at the Bloch sphere represents a state. You can use those geographic coordinates like longitude and latitude. The situation is a bit more complicated for arbitrary n. Then the space of all states, they are of course normalized, and we consider equivalence classes up to a phase. So then this space is not a sphere. It is a complex projective space with 2n-2 real dimensions. But now look, the space is isotropic, like a sphere. So you could say, well, all states are equal. So there are no extremal states. What I'm going to talk about, all states are the same. In some sense, this is correct point of view. If we have no additional structure, then the space is really isotropic. It looks like as a sphere. All points look the same. No points are distinguished. However, if we impose some structure to the system, then we can say that all quantum states are equal, but some of them are more equal than others. For instance, if we consider a composite 2-qubit system, so I have here 2 pairs, one is left, one is right. So I have a system and I can decompose it into 2 parts. So now, of course, we can distinguish separable states, so product states, which are distinguished. And on the opposite end, we have maximally entangled Bell states. So obviously, they are special states. They are, I could say, more equal than other states, just because I observe that this system, physical system, we can split into 2 parts. So I distinguished left subsystem and right subsystem. So then we can look for those extremal states, for instance, like Bell states, which are most entangled states for 2-qubit systems. They are useful in several applications, like in quantum information, in different protocols. So this gives us a good motivation to study them. So to remind you some simple definitions, if we have bipartite systems, so separable pure states are just of this tensor product structure, entangled are not of this form. Simple case is the famous Bell state. We see it is not a product state, so 0, 0 of course means 0 times 0, but here we have a sum, so a superposition of 2 states. So therefore this is not a product state, it's entangled. In fact, it's maximally entangled. Why? Because partial trace of the projector is maximally mixed. So technically we can take any state and expand it in any product basis. So we have here this matrix of coefficients. And now we can compute singular values of this matrix. Let's denote them by lambda, and they appear here in this so-called Schmidt decomposition. Instead of double sum here, we have a single sum here at the expense of changing both bases into I prime and I double prime. And now, because the state is normalized, so norm of C is 1, all those numbers, lambda, let's call them Schmidt values, they sum to unity, so they define a probability vector. This probability vector is nothing else as eigenvalue, so spectrum of partial trace. And then to characterize the degree of mixing of this vector lambda, we use the standard von Neumann entropy, and then we say that the entanglement entropy of the bipartite state psi is equal to the von Neumann entropy of the partial trace. So minus trace sigma log sigma, where sigma is this partial trace, or Shannon entropy of the vector of Schmidt coefficients. By the way, if something is not clear, not mentioned, not explained, please do not hesitate to stop and to ask questions right away. We can easily generalize this setup for higher dimensions. If I have 2 qubits, so 2 subsystems of size d, I define the generalized Bell states. Look, it consists of, there's a sum of d terms with the same prefactor. So it means that all singular values lambda are equal. They are just 1 over, lambdas are 1 over d. So then this state is maximally entangled because the reduced state, so partial trace, is maximally mixed. And then state psi is maximally entangled if partial trace is maximally mixed. So this matrix C of coefficients defined before is unitary up to rescaling. Then, of course, all singular values of a unitary matrix, so they are just a radius of eigenvalues, are equal to 1. By the way, look at this state. I can call it Hadamard state, 0, 0, plus 0, 1, minus 1, 0, minus 1, 1. So look, you have 3 pluses and 1 minus. Maybe it's not easy to see, maybe it is. It is equivalent to the Bell state. It is really a entangled state. Why? Because this matrix, if you compute this matrix, is 1, 1, in the second column, 1, minus 1. So just a Hadamard matrix is unitary. So in short, for bipartite systems, everything is simple. We write down the state in a product basis, and this matrix C characterizes entanglement. It's enough to compute entropy of the vector of singular values of this matrix C to describe entanglement of such a state. This is simple for a bipartite system, like 2 objects. But if we have more, like 3 or more, then the situation is much more complicated. Why? Okay, multipartite are more complicated than bipartite. Mathematically speaking, well, there is a huge difference between 2 and 3. So here, 2D object is, okay, easier to describe than 3D. So multi for me is 3 or more. And why it is so? Well, I have a simple algebraic argument. If I have a state describing 3 subsystems, A, B, and C, then I can expand this state in a product basis as before. But now, instead of this matrix Cij, I have a tensor labeled with 3 indices, I, j, k. And here, simple algebraic arguments enter the game, because it is easy to diagonalize a matrix, compute its rank, find its singular values, and so on. And for tensor, everything is much more complicated. Even the notion of a rank of a tensor, okay, there are many different definitions, and they do coincide for matrices. For tensors, it is much more difficult, and to compute a tensor norm is also more complicated than to compute the norm of a matrix. So now, having such a family of pure states of 3 or more partite system, we can pose a legitimate question: which of those states? So let's say we have n subsystems with d levels each. So in the jargon, there are n qubit system. Which of those states is the most entangled? Well, for instance, for 3 qubits, we have GHZ states. It looks like this, so simple generalization of Bell states. But we also have a W state. It consists of 3 terms. And as you see, they are somehow different. They are not equivalent. So we can ask which of those states is more entangled. And the answer is, as you can guess, simple. The answer is we do not know. Why? Because it depends. It depends which measure of entanglement you take into account. So in principle, the answer to the question which is the most entangled is still, the question is not well specified. It depends on the measure of entanglement used. Before I continue, I will make a short combinatorial digression. So look, I will recall an interesting paper by Zauner, the Gerald Zauner. In fact, it was a thesis from 22 years ago. And in his thesis, basically, he, well, I would say, made the foundations of quantum combinatorics. I will tell you what I mean about it. But first, well, I will make a simple example, classical combinatorics. We have a lot of cards, like here I have a few cards, but let's imagine we have 16 cards. We take 4 aces, 4 kings, 4 queens, 4 jacks, and we want to arrange them into an array 4 times 4, such that in every row and every column consists only a single card of each suit and each rank. A simple question. Is it simple to find the solution? How do you think? Are you there? I will take a sip of tea, and please let me know. Are you there? Yes, are you alive?
Yeah.
Yes, Carol. Yes, we hear you. We hear you.
Very well. So here's a solution. As you can guess, it exists. Look, we have 16 cards, and we place them in such a way that in each column, each row, there are exactly one card of each suit, each rank. So this is called in mathematical notation the two mutually orthogonal Latin squares or Greco-Latin squares of size 4. Greco-Latin because Euler used Greek letters to describe, let's say, rank of the card, and Latin to describe the color. And mutually orthogonal means that each card basically is different. So look, such scheme exists for 16 cards, and you place them into a square of size 4. You can have such squares of size 3 and 5, but you will not have them for size 2. Why? If you take two cards, like two aces, now look, you have two aces, and you want to put the king. You cannot put it neither here nor there. Why? Because a rule that there are no two cards of the same color will be violated. So you see, with 4 cards, it's easy to see that there are no two orthogonal Latin squares of size 2. And there exists, as I showed you, two orthogonal Latin square of size 3, 4, and 5. You can believe me. And with 6, there are problems. There was a famous problem attributed to Euler. There was a very nice practical application, in a sense, a military application. The idea was he was, then employed by Tsar, working in St. Petersburg in Russia. So of course there was a lot of officers and military parades. And the question was, if you have 36 officers of 6 different ranks from 6 different units with different uniforms, can you arrange them in such a square 6 times 6, such that in each row, each column, all uniforms are different? So mathematically speaking, is a question whether there exists a Greco-Latin square of size 6. And even Euler himself was not able to prove that it doesn't exist. But of course, he knew that it doesn't exist. So it was only a conjecture by Euler. And therefore, this question is now called the problem of 36 officers of Euler. And we know that the problem has no solution. We know because 21 years later, Gaston Tarry, a French, he was not a mathematician, he was a lawyer. He published a paper where basically he solved the problem in a negative way, because his main feat was to show that there are many thousands of possibilities, but he could reduce those thousands to, let's say, a few hundreds, and then one by one he could check that no solution exists. So, by the way, have you ever seen such a game for kids? So look, you have 36 pieces, and you have to put it into such a square that in each row, each column, there are different colors, and then you see there are different heights of those pieces. So in a sense, they correspond to the ranks of officers. So look here at this picture. By the way, this it's called 36 cube, the world's most challenging puzzle. So this looks like apparently a solution of the problem of Euler. Why? Because there is, you see, in each column, each row, there are different colors and there are different heights. So this almost proves that Euler was wrong. But of course, only because mathematically Euler was correct. And this is, as you can guess, maybe not cheating, but this is physical imperfection. So colors are well done, but here the trick is that 4 of those pieces, they look to be of height 4, but in fact they are of height 3 or something like this. So with this help, this problem has a solution. But classically, I can assure you this original mathematical problem of Euler has no solution. By the way, how do you think why it has no solution? Well, mathematicians will know, because 6 is 2 times 3. So it's not a prime number. And 4 is not prime number either, but it's a power of 2. And 6 is a first number, which is neither prime nor a power of prime. And therefore, in mathematics, there are many, many effects which are related to number 6, which is special. For instance, there are not so-called finite planes consisting exactly of 6 different points. And no Greco-Latin squares of size 6. So now look, we will go back from Latin squares and classical combinatorics to quantum. I will go back to the case of many systems, and I will now define a single measure of entanglement, and I will define a very simple notion of absolutely maximally entangled states. Amen. By the way, this problem was also studied by a Nobel laureate. You know the names of the Nobel laureates, perhaps? So I can show you here the paper fact key. There was another paper by authors were Severini, Pascazio and Parisi. So Parisi got a Nobel Prize, and interestingly, he was also working on this problem. They called them maximally entangled state. So the idea was simple. We look for such states which are maximally entangled, bell-like, for any choice of splitting. So let's assume we have 4 parties, and we say, if we split them into bipartite like this, they are generalized Bell states, maximally entangled. But if we swap some subsystems, this property should be preserved. They are also maximally entangled. So basically, there are 3 different, for 4 subsystems, there are 3 different splitting of 4 elements into 2 pairs. So AME, absolutely maximally entangled states, analyzed also by Parisi and others, are defined by the way that this entanglement is maximal. So if you take, in general, n objects, if you perform partial trace over half of it, you will have maximally mixed state. This is a basic notion in my talk. So now let me ask you, do you understand this idea? So examples are simple. For Bell state, it is just, okay, it's called one uniform. So it is just called state AME state of 2 qubits. So they exist. One uniform means that if you perform partial trace over one subsystem, the remaining state is maximally mixed. However, interestingly, Higuchi and Sudbury proved that there are no such states for 4 qubits. However, there exists such states for 4 qubits. There exists such state for 6 q-quarts. So now notation is following. 6, 4 means 6 subsystems of 4 levels each. And now my question is, what about AME state for 4 subsystems with 6 levels each? Whether they exist. So I can tell you, nobody knew even a year ago whether they exist. And I will show you a relation to the problem of Euler. Namely, I claim that the state, absolutely maximally entangled state of 4 qubits exists. So here it is. Here it is. This is the state of 4 qubits. So we have 4 subsystems and 3 levels each. So I label them from 0, 1, and 2. And this is a very peculiar state. You can check, it's not so difficult to check, that it satisfies this property if you, out of 4 subsystems, choose any 2, perform partial trace, so average over 2 subsystems, put them away, the remaining state is maximally mixed. And now, how to relate it to our combinatorial notion of Greco-Latin square. So here is a really Greco-Latin square of size 3. So you see Greek letter, Latin letter, it corresponds to such a composition of 9 cards. Now I need to use only 3 aces, kings, and queens, or for information science, we can use just those numbers. We can label 2 letters going from 0 to 2. So you see now that this is exactly the same Greco-Latin square. And the recipe to write this special AME state is very simple. First 2 digits is just address, like 0, 0. And second 2 digits, those red numbers, are given by the contents of this box. So first is 0, 0, 0, 0. Now the second box has address 0, 1. We go here, we look, king of clubs is denoted by 1, 2. So we put 1, 2 here. Third box, queen of diamonds is denoted by 2 and 1. So we put here 2 and 1. Now second row is represented by those numbers, and it gives us this line. Again, first 2 numbers are just address, second row, and second 2 digits here are taken from this line, while the third one corresponds to the third line here. So now a key question. Do you understand the relation between this object, Greco-Latin square, and this state? Now the key argument is the following. The fact that in each row, each column, there exists only one ace, or one king, one queen, or one color of each card implies that for this state, if you take partial trace over whatever two subsystems out of 4, you get maximally mixed state, you get maximal entanglement. Therefore, this condition of Greco-Latin square is crucial. By the way, it's also possible to, out of such a state, why they are useful, you can immediately write down a quantum error correction code, which is written here. So this gives you a relation between our states and the classical problem, combinatorial problem of Greco-Latin squares. So now, why do we care about those AME states? Because of different applications like quantum codes, teleportations, and things like this. And then there was a paper, even a table online by Huber and Wederka. So here are different local dimension and different number of parties. So basically, green means such states exist, red it doesn't exist. So here, this question mark corresponds to local dimension 6 and local number of parties 4. So 4 Q hex. So this was the open case a year ago. So the key issue is whether such strange state exists. And now we cannot, since having Latin square, we could easily write it down. But we know because of Euler that such a solution, such an object does not exist for n equals 6. So standard Latin square will not exist. But maybe there is some new notion of quantum Latin square. So here I'm pleased to quote a paper done together with Dardo Goyeneche. So you see here, there's an Argentinian liaison. Even it was done, this paper, as he was still in Poland. So we somehow managed to generalize this notion to mutually orthogonal quantum Latin squares. So Latin square, you know how it looks like? Quantum is, instead of having numbers, we have states. So now we have a table of, here in this case, 16 states, such that in each row, each column, you have an orthogonal basis. So in a sense, they are different objects. Well, to have a pair of quantum Latin square, we need to find a d square states in the bipartite Hilbert space. So you have d square states, we can put them into such a square. So in fact, it's convenient for me to take this state and, as before, decompose it in a product basis. So each state corresponds to such a matrix, CKL. So now I have d squared those matrices, and now the orthogonality constraints are the following. This is a block matrix, and then it's block unitary, in the sense that if you consider a sum over I over j, then this, so basically row-wise sum, each vector of blocks is orthogonal to another block. So there are those two conditions. And then if those conditions are satisfied, they are just conditions similar to standard definition of classical orthogonality, then the following state, look, the following state is now 4-parity state, ij and phi ij defined here, which are defined by this huge matrix, they form an AME state. So absolutely maximally entangled state of 4 subsystems with d levels each. Well, so some other remark is that this state, you can be represented like this. So this is here a entangled state, Bell state of 4 Q hex, and now you look for such a unitary matrix which entangles now subsystem, let's say A and B together. So this unitary matrix which does the job maximizes so-called entangling power. So now here's a picture from Krakow. Some of you were here, could enjoy it. I presume I have only a few minutes left. So I will now show you how to solve the problem. Which problem? To find the absolutely maximally entangled state of 4 Q hex. So here is this solution we know for 3 Q trees. So we know that from this pattern, we can formulate such a state. So there's a matrix U of size 9. It's a permutation matrix which tells us where to put different cards. It's matrix of size 9. And it has the following property. If we perform partial transpose, it's also a permutation matrix. If we perform reshuffling, so reorder elements of those matrices. So if you use this tensor notation, we reorder a sequence of indices, then it is still permutation. So those reorderings correspond simply to different splitting of the entire systems into 2 subsystems. We have 3 such a splitting, like this, and like this. So we wish to maximize this entangling power, and then here we use the following variables. For any U, we define this entangling power, which can be defined by the E is just linear entropy of the vector of Schmidt coefficients of the operator Schmidt decomposition of U. S is the swap operator. So for any U, I can explicitly write down, compute such a number, and then I can compute the dual number you see here is plus and minus. So this is this, it's called typicality of a gate. And I wish to maximize this number. So look, here is a very nice pattern, a square 6 times 6. We use now 36 cards, and you see it's almost a solution of the problem of Euler. Why almost? Because I have 2 queen of diamonds and 2 jacks of hearts. And this point is a permutation matrix which corresponds at some point here. So now I want to use this point as a starting point for my procedure to look for the optimum. Optimum will optimize the entangling power, so it will be at the right edge of this allowed space. Yes, I'm going to finish very, very soon. So we did some numerical search in the following way.
Carol,
Yes.
you can go on. You can go on, but you shall will take off time for questions. But
so
it's fine. Perhaps it's better if you finish, because it's better.
The idea is following: we want look for such a matrix, which not only is unitary, but also after reshuffling and after partial transpose is unitary. And the idea is the following: we perform such an operation, and then it's in general not unitary matrix. By the polar decomposition, we look for a closest unitary, and we continue. And then very often, this procedure is not convergent, does not give anything interesting. However, if you are lucky, if you find a good starting point, so look here, this is another approximation to the solution of problem of Euler. Why it's not a good solution? Because you have 2 jacks in the same column. And then starting from some of those permutation matrices, this here you see a trajectory in this space. Strangely enough, it converges just to this corner. So corner is 2 unitary matrix we're looking for. So it's a matrix of size 36, which enjoys very special properties. Not only it is a unitary matrix, but also the shuffled U or partial transpose are still unitary, which means that it defines such a absolutely maximally entangled state. So then we get some numerical values of this matrix 36 times 36 were difficult to understand, but fortunately we had a freedom of taking local operations of size 6, and we find a simpler form, and then after a simpler form we can, after nice permutation, we can bring it to the block form, like 9 blocks of size 4. And now, since it should be unitary matrix, in each block we could write unitarity conditions, and then we could solve them analytically, and we could prove that also after partial transpose and after reshuffling, it's still unitary. So here comes the result. Results analytical. We can call it a golden state. Why? Because the golden ratio, you know the number, 1 plus square root of 5 over 2, appears in the solution. So basically, Here you see there are those 9 blocks of size 4, and all of them are functions of 3 numbers A, B, and C, which are known analytically, and the phase omega, and omega is just the root of identity of order 20. So you have here different powers. So basically, now this solution is found analytically. It is related geometrically to this pentagon. So it allows us to write the solution of the Euler problem in the following sense. So we know such a square 6 times 6 does not exist if there's only a single card here. But now look, we allow those 2 cards to be entangled. We are joking that the officers are entangled, like general with a colonel. So if we allow king of spades to be entangled with ace of clubs and have such a structure, it corresponds just to the quantum version of orthogonal a pair of quantum orthogonal Latin squares. And now this golden Ames state corresponding to 36 officers of Euler has very, very peculiar property, the following. If you choose any 2 dices and measure a state of 2 dices, so you look, each of them lives in the subsystem of size 6 because a dice has 6 faces. So it conveys a number of 1 to 6. Then after this measurement, you can know what will be the outcome of the measurement of the remaining 2 dices. It's like in the Bell system, Bell state. So I think I should finish now. So main message is that we could study strongly entangled extremal multi-parted quantum states. Extremal because they maximize, for instance, this entangling power and many different properties. And we found such new states which are useful for many different purposes like error correction codes or quantum communication. So in short, we have a theorem that absolutely maximally entangled states of 4 subsystems with 6 levels each do exist. And strangely enough, we achieved this result this year, 2021. So exactly 121 years after Tari's paper was written, 121 years, so 11 square after the problem of Euler was posed. And then our solution implies that there is a solution of a quantum analog of the famous problem of 36 officers of Euler. There exists an optimal bipartite unitary gate of size 36, which maximizes entangling power. There exists a perfect tensor with 4 indices, each running from 1 to 6, such that if you exchange indices, the unitarity does not change. And such tensors are now used in tensor networks or in study of bulk boundary correspondence. And this state allows us to write down the quantum error correction code, which allows us to encode 1 Q hex, so physical system with like a dice, quantum dice, into a 3 such subsystems. So I hope that I convince you that such extremal quantum states can be useful. Thank you very much for your attention.
Thanks, Karol. Thanks for this wonderful talk. So now we have some time for questions. Please, if someone has a question, write it down in the chat and I will pick it up. So if no one has a question, I have a question, Karol, because
yes,
from some time ago, it's lurking in my mind the idea of applying maximum entropy principle to study entanglement, because it seems that for very relevant entangled state like the AIME, so for some subsystems, you have a maximization of entropy for the subsystem, because you said maximal mixture, you can read it as a maximization of entropy.
Sure.
What do you think about that idea? Do you know of any work of someone doing that?
Of course, it's a very good question, but this is exactly what we are doing, because we want to maximize entanglement. So in a sense, the entropy of entanglement, but look, with respect to this partition, but also with respect to this partition, and also with respect to this partition. So in a sense, we want to optimize the sum of 3 different entropies, which characterize a single state, because those 3 entropies, we have 4 subsystems, and they are correspond to splitting of the entire system into different subsystems. Yes. So our research was just to optimize, to maximize the sum of free entropies which correspond entanglement with respect to different splittings.
Okay. I see. Thanks. Yes, I will have to. Fortunately, the talk is recorded and we will publish it on the website, and I will see it again, of course, many times to try to understand all the details.
Yes. Thank you very much.
So thanks.
So
Thanks, Carol. Thanks, Carol.
I'm also pleased to recommend you this paper, which is now available on the archive. And I emphasize that the Adam Burkhardt had a, Suhail Rater found the state and Adam found its analytical form.
Okay. We will check it carefully. Well, we thank again, now there's no more time. We thank again Professor Sikowski for this great talk and staying here with us again.
Yes.
We are really thankful for you. So we give some internet claps.
Thank you very much.
Sikowski. Thanks. And now we call the next speaker of this morning session. Please start to share your screen if you can. I think that.
Hello, Mariela. Nice to see you. Yes.
Hello, everybody.
Hello,
Carol.
Yes.
Hello.
Very
Yes,
nice,
yes.
very nice talk.
Hi,
Thank you.
Walter.
Hello.
Do you hear me?
Yes, Pedro.
Yes. Please start to share your screen so we
Okay.
check whether everything is working, and then we start. So you can try to share full screen. Perfect. Okay, so the next speaker of this morning session will be Professor Walter Lamberti from the University FAMAF of Córdoba, Argentina, and he will speak about a precurstis approach to distances between quantum states. Please, Walter, go on.
Okay, thank you very much. I would like to start saying that 10 years of this event is a very effort from several young people, Federico, Martin, Olympia, and several others. I will like to emphasize the effort to keep this meeting every year. Unfortunately, for the pandemic, we are not possible to share coffees and music and other events, but congratulations for everybody to keep this event going on. Okay, I will start the talk. The name Procustes came from a mythological character. The person is Procustes, that is known in mythological Greek as the master of deformation. Okay. Well, what have to do this with quantum mechanics? I will try to explain in the follow. Let's suppose we are going to a quantum shop and we need a quantum state rho. The person in charge of the quantum shop should take a stay from the set of matrices known as density matrices, which has these properties. H sub n is the Hilbert space of our physical system. Rho are density operators, which are semi-definite positive operators with trace equal to 1. Okay. The problem is the following. We pay for the state we want, rho, but probably we get a state sigma. Then we will notice the difference. Is the quantum shop trying to scam us? In general, due to quantum foundation, we can be lenient with the quantum shop if rho and sigma are close, because in general, rho and sigma are not perfectly distinguishable. But what is the meaning of close? In the case of the desired state is pure, we only need to maximize the overlap this in order to distinguish between rho and sigma. But in general, if the state is a mixed one, we need to measure the distance between rho and sigma. The notion of distance has to do with the notion of a metric space. Yeah, in general, we can define a metric space as a topological space with a binary function D from the Cartesian products of X into the real number, the positive real number, with these three properties: positivity, symmetry, and the triangle inequality. In this case, the function D is called a metric. In some sense, this notion of metrics is non-local, because we are not assuming that X and Y are close. Yeah. In general, we are working in a topological space where the notion of continuity or proximity are defined. Okay. So therefore, we mention this binary function as a non-local concept of metric. There are several examples of metrics in or defined between quantum states. The most or the best known examples are the Hilbert-Smith, the trace distance, the Buress, and the Buress is particularly interesting because it's defined from the concept of fidelity, which is defined in this way. This quantity looks very complicated to evaluate, but from a result of JOSA, it is possible to evaluate the fidelity from the concept of purification. What is the purification? Is a map that allows to represent the state, the mixed state, rho and sigma, as pure states. And it's very important to remark that the fidelity can be evaluated experimentally. In many experiments about teleportation or dense code, etc., this quantity can be experimentally evaluated. Well, what is necessary to have many distance between quantum states? there are some formal questions, for example, associated with the fact that the geometry of the space of the states depends on the metric used. When I talk about geometry, I want to say aspect like the geodesic or the curvature or many other geometrical properties. Even when you have the same space, the geometry properties depends on the metric you use on this space. This is a very important point. Another aspect that justify to have many distance between quantum states are some practical aspects. For example, in this paper, this is a recent paper, the use of some particular distance can be evaluated from experimental setups. So it's not the same to evaluate experimentally one kind of distance between quantum states. I mean, if you use one kind of distance, probably you can evaluate experimentality, but if you use another, the experimental evaluation may be quite difficult. And this is another important result showing that some properties of a distance, for example, in this case, the Hilbert-Smith distance, depends on the kind of dynamics under study. You can prove that if the evolution is unitary, this distance have this property, but if the evolution is of Lindblad kind, that result is not true. So there are several other motivation to study different kind of metrics, but I think these three are enough to mention, okay? Well, there is a connection between information and how you can distinguish two objects. For example, to distinguish a cat from a dog, you need to have different kind of information about each one of these animals. It seems similar, but if you know some particular aspect, you can distinguish in a better way both pets. So there is a connection between metrics and information theory. In that sense, this quantity that we were working a lot of time, known as the Jensen-Shannon divergence, has its origin in information theory. Here, if we start from two probability distribution, P and Q, and we can evaluate the Shannon entropy of the mixture of both probability distribution, and we can evaluate this quantity, okay? In fact, this quantity have been used in several contexts, And therefore, we think it's a very relevant example of distance between probability distribution from the information theory. This divergence is a particular case of the Caesar family of divergence. A Caesar divergence is defined in this way, where we suppose that f is a convex function and at 1 is equal to 0. In the particular case of the Jensen-Shannon divergence, the function f is this one. There is an interesting connection between this divergence with the geometry of the simplex of discrete probability distribution. You can define the simplex of probability distribution as a manifold in the sense of the word manifold I'm talking about is in the sense of the differential geometry, and it is possible to the simplex P to give coordinates, and in this manifold there exists a particular metric known as the Fisher metric, which is represented in this way. But it's not important the details, but the important fact here is that we can provide a Riemannian structure on P from the Fisher metric. When you have a local metric, I emphasize local in order to distinguish with global metrics, because if you have these coefficients, you can evaluate the distance between two close points in the manifold P. So only in some particular case you can evaluate the distance between two separate points. When you know these coefficients, you can evaluate the notion of parallelisms in the manifold, the notion of geodesics, the curvature, and several other geometrical properties. Okay, so if you have a local metric, let's say the Riemannian manifold, you can evaluate this quantity. So if you want to evaluate the distance between 2 points, you can evaluate by using this curve or this one. In this case, when you use the line between P and Q, you evaluate the geodesic distance. In the case of the Fisher metric, it is possible to show that the geodesic distance is given by this expression. And in the context of quantum mechanics, I will back soon to this point, but in the context of quantum mechanics, this distance is known as the Wutter's metric. So it is possible to show that the Jensen-Shannon divergence can be written in terms of the coefficient of the Fisher metrics in this way, where this is the metrics and this is the connection associated with this metric. This is known as the Christoffel symbols, that can be evaluated from the metric coefficients. And to higher order, the terms that here we can evaluate have to do with the curvature of the manifold. This is the relation is important because we can relate a global distance as the Jensen-Shannon divergence with local geometrical properties. A very important point of the Jensen-Shannon divergence is that its square root have been shown to be a real metric in the sense of the definition of a metric space. Yeah, that means the simplex P with the square root of the Jensen-Shannon divergence is a metric space in this sense. Okay. One aspect, and one is an important aspect, is you can have a lot of distance between quantum states, but not always it corresponds to metricals in the sense of a metric space. Well, let's continue with this point. If you take the Euclidean metric, we work at this moment with the simplex space. If you took the Euclidean metrics, it can be written in this form, where the function g is given by this expression. Let's see this structure of the Euclidean distance between two arbitrary probability distribution. If you write the Jensen-Shannon, alternatively, it can be written in this form. Yeah, and if we compare the structure of the Euclidean metric with this expression, we found that they are similar. In some sense, that is the main point, the Jensen-Shannon divergence is a deformation of the Euclidean metrics. And they share two aspects very significant. The square root of this expression is a metric, and the square root of this expression also is a metric. So here appears the concept of deformation. Yeah. So we can think in something like a super operator that take Euclidean distance and modifying certain parameters, we can go through several other metrics. In one extreme is the Euclidean metrics, and the other extreme is the Jensen-Shannon metric. This idea was introduced by Burbea and Rao in 1982, but we try here to give a different perspective or approach to this kind of divergence. Particularly, we want to extend this idea of deformation to the realm of quantum states. So we can introduce this family, this new family of divergence, by changing the function g. Let's recall that in the Euclidean case, G is the linear function, and in the case of Jensen-Shannon is the logarithmic function. So we can introduce a family of divergence by changing G. Whenever this product is a convex function. Well, if we require this property, it is easy to show that it's defined positive as symmetric, but in general, we cannot assure that the quantity square root of this divergence is a true metric. We will walk to this point later, okay? This is a very important point because we are searching for metrics in the sense that it satisfies the triangle inequality. It had been shown that the Jensen-Shannon divergence has been useful to analyze several problems in statistical physics and in quantum mechanics. For example, this divergence has been used to study time series, networks, multi-layer networks, quantum entanglement, and several other topics that makes this divergence a very significant one. Okay, there is a theorem, a classical theorem from harmonic analysis, known as the Schoenberg theorem, that give a characterization that can be applied to indicate if this kind of divergence really its square root of the divergence is a true matrix, and the condition that it's required is that certain inequality be satisfied. In the previous definition, the characterization of the Schoenberg theorem required that this kernel, technically is known as a kernel, satisfies this inequality. Of course, this inequality depends of the function G. Yeah. This is an important aspect. Only we can assure that the square root of this divergence be a metric if this inequality is satisfied. It does not important the details, yeah, but only to mention that what is important in the definition of a new divergence. Another point is very significant. We have defined this new family of distance, and we want to compare with the Caesar divergence for two very close probability distribution. We can approximate the Caesar distance between P and P plus dP in this way. And for the divergence D sub G, we can approximate in this form. Whenever we assume that the G function be one differentiable. And here emerges a very important result, because the only dg, remember this expression, the only dg divergence, that is a Caesar divergence, is the Jensen-Shannon divergence. So we really have a new family of divergence, only coincident with the Caesar divergence in the case of Jensen-Shannon divergence, okay? This is another important aspect of the this family of divergence. Another point of the Schoenberg theorem is that it, under certain conditions, it is possible to map the simplex of probability distribution into a Hilbert space. In order that this map allows to use the norm induced by the inner product in the Hilbert space and relate this quantity that is a property from the Hilbert space with the square root of the G divergence. Yeah, well, maybe difficult to find this map, but this is a very important result. There is a connection between the inner geometry of the Hilbert space with the Riemannian or the metric structure of the simplex P. Yeah. In some cases, it's possible to determine the function phi, but in many other cases, it's difficult to find this map. But this is a valid, general valid result. Okay. Well, I don't know how I am the time. I suppose I have 10 minutes.
Yes,
So,
now you are on time. So now you enter the time for questions. So you can go on a little bit, but there will be less time for questions. Yes.
Okay, thank you, Federico. Okay, well, the other step in our work have to do with the extension of this classical divergence. I mean, by classical, the fact that we are evaluating this divergence between two probability distributions, and the question is how to extend to a distance between quantum states. Well, the natural extension of TG to the realm of quantum states is through this expression, where the function f is this product. We require, as before, that this product is a convex function, and here we operationally we have to evaluate the eigenvalue of rho, the eigenvalue of sigma, and the eigenvalue of the mixture. And from that eigenvalue, we can evaluate this tracer. Okay? There is a theorem. This is another very interesting result. When you do this extension to this classical divergence to quantum states, there is this theorem that affirms that the square root of this divergence is a true metric in the sense that it verifies the triangle inequality for the particular case of 2 by 2 density matrix. Yeah. in particular, as I said before, the Jensen-Shannon divergence is a particular case of this kind of divergence between mixed states. But recently, by two authors, one of these authors is Daniel Birostek, that in 2021 showed that the previous result for 2x2 matrix, and this other author in this year has made advances in the proof for dimension 3. And this author was able to prove that the Jensen-Shannon divergence is a true metric in the sense that its square root is a metric for any dimension. Yeah, so we have a proof that the square root of the Jensen-Shannon divergence between mixed states is a true metric for any dimension, and this kind of divergence is a true metric in the sense that it's a square root for dimension 3. For higher dimension is an open problem. Yeah, and we are working on this point. Okay, so in order to conclude, we have introduced this family of divergence between mixed quantum states. Its square root is a true metric for dimension 3, and the general proof of the metric character of this divergence is still being an open problem. Okay, thank you very much. Any question or comments?
Okay. Thanks, Walter, for this wonderful talk. We are very happy that you are here speaking, because you were one of the professors that supported this conference from the very beginning. And if we are here, all of us here together discussing quantum theory is to a great extent thanks to you. So there is a question in the public about this. Professor Decio Krause asked, if do these quantum metrics obey the Hausdorff's property? In other words, can two systems always be discerned by open sets?
Yeah, in fact, I have to mention another important point. From a physical point of view, when you have a distance between, let me, for example, here, for example, when you have this kind of divergence between mixed states, you must require that, insist from a physical point of view, you must insist, we must require that this function be monotone, in the sense that if you apply a map, for example, a CP map to both states, you must obtain inequality between this quantity and the corresponding after you apply a CP map. For example, that has a very interesting interpretation, because from a quantum point of view, you can describe the evolution or the general operation of a quantum state from a CP map. The most general evolution is not given by the unitary evolution. So that property may be valid for some particular function f. It is difficult to prove that in general that property of monotonicity may be valid for any f. Anyway, we are working on that point, and we are trying to characterize for which kind of f function the monotonicity is valid. Yeah, I don't know if I answered the question, but the answer have to do with the study of that kind of property. Yeah.
Okay. Okay. So we are on time. Thanks, Walter. Decio Krause says thank you in the chat. So I think you
okay, but Prof, yeah, if he want, Krause can write me and we can discuss that point longer. Okay.
Yes, perfect. I can give him your email. Okay.
Okay.
Perfect. Great.
Thank you, Federico.
Thanks, Walter. Thanks. So we are on time. So now we have 10 minutes break, and we come back here at 10:30 for Professor Krause's talk. Remember that all times displayed in the program correspond to Argentina time. So see you in 10 minutes.
Do you remind here?
Please, Walter, to share.
I would like to try to put my slides in to see if they work.
But Walter should take off.
Okay.
Yes, please. That's the same problem. Oh, Jesus Christ.
Does it works?
No. I can't put my file here in the place where the disponible files appear. I don't know which is
wait. Are you using a Mac system or a Windows?
Yeah, Mac system.
Mac? Yeah. Okay. So as I understand, what you should do is when you put share screen, you can choose the option share desktop. And if you do that, you will share
desktop.
Yeah, share desktop, like desktop one or whatever. It should have a name. Yeah.
Yes.
And then if you do that, it will share all what happens in the screen of your computer. So everything that you have open, just close it and leave open only.
I did it. Are you seeing my screen?
No.
Yeah, then it doesn't work.
That's really strange.
Let me see if I can find it.
But also let me, because the Mac system asks for some some permissions. Let me see. Mhm. Okay. There's a caveat. Listen, when you put a share screen, you know, the green
Yeah. Share
button
screen.
that appears. What do you see exactly?
I
If you do
I
it right.
see. No, I see some possibilities. Desktop one,
Okay.
blank possibility. iPhone, find unknown, and
Yeah,
please.
I think, yeah, but you don't see a something that says allow Zoom to share your screen or something like that. You
No,
don't-
no, no.
No, okay. So I think that it's already working. But what happens if you click on desktop one?
Nothing.
Nothing.
It says permitir que o Zoom compartilhe sua tela. Então, eu permito abrir.
Yeah, you need to allow that. Yeah.
Yeah,
allow.
I have allowed it.
And
Then it appears some possibilities of contacts and pictures and so on, but I cannot access my file.
yeah, but perhaps okay, you don't see your file, but you see desktop, and when you press on desktop, nothing happens.
No.
No, strange. Okay.
It enters in the preference of the system.
Okay. System preferences. Okay, go there. Okay. Yes, enter system preferences.
Yeah,
Now,
I am in.
You should check the box next to Zoom. There's a Zoom, when you enter system preferences, there's a box where there's a Zoom symbol. Do you see it?
No. Zoom, no. No.
On the right.
No,
Let me show you my screen. Let me show you my screen.
Yeah, please.
Let me share screen, and let us see if something like this happens here. Share. Do you see my screen?
Yeah.
Okay. So you put share screen, the green button.
Yeah.
Then
Okay.
you have the desktop. You choose desktop.
Yeah.
And then you will be asked open system preferences.
No, it doesn't appear to me.
Doesn't happen. But you don't go to here or something like that. So
No.
You don't see any of this.
No.
So okay.
Let me see the Zoom if you have some possibilities here.
Yeah.
What happened when you share desktop one? What happens?
What happens?
Yeah. Fede, stop to share. Stop to share. Fede. Okay.
Let me see. I'm sharing the screen. It appears some possibilities. Desktop one and other things.
No, click on desktop one. Click on desktop one.
Okay, then appears allow the Zoom to share your screen.
Yes.
I'm enabling it. Okay, then it's recording, Federico. Well, it's me.
Okay. Yeah, I see. Nothing happens. Perhaps, Decio, what we can do is that you send me your presentation.
Yeah, again.
Yeah. It's annoying, but we can do that.
Yeah, it's alternative. I will do it because we are in time.
Wait a minute. I will do Decio co-host, maybe.
Yeah.
That's
very
important.
Maybe.
Otherwise, it doesn't work.
Yes. Keep me the co-host.
Yeah, you are co-host now.
Try again. Try again.
Who's speaking, Martin?
Martin.
Hi, Martin.
Hi, Decio.
So now try again, all the same again, because now,
please. I will try again.
Being co-host.
Co-host.
It is strange though. Yeah.
Find it or no. Share. Not yet.
No,
you are co-host now.
Yes, but not happening.
Yeah, but nothing happens. No, I see. It's.
I will send you, Fede, or for your bot.
Okay.
I will send you, Fede.
Let's do that. Yes.
Yeah.
Send me by email. Okay.
Oh, Jesus Christ.
It's very strange.
Don't worry. We will coordinate.
No, never. I never can use Zoom and share.
It will be indistinguishable from
Let's see.
from your share.
Look at.
Wait, huh? Give me a time. I'm just sending.
Fede, cuando comparta, muteate por las dudas, así aparece la cara de
Sí,
Decio.
sí, obvio. Okay. Let me go. Let me put it in a good folder. Otherwise, you will get lost in my
Yes, but
infinite
if I
desktop.
knew which folder I should put my file, it will be easy. But I don't know which folder is the correct one.
No, but no, because it should read it from what you are sharing on screen, because usually the system detects what is open
Yes, I
and what is
agree.
closed.
But,
Yeah.
archives.
So I think that perhaps some.
Oh, perhaps in Dropbox.
No, well, it might be, but I don't think so. Wait. Let me open this with Sumatra PDF. So we can safely apply Control L. Well, now I will share. Okay. I'll share, okay? Let me see how we are on time. Okay, we are on time, so we should start.
No, Fede,
So-
I can see your screen, eh? I can't.
No,
I
pará,
can't
por eso, pero pará. Wait. Be quiet, Martinete, be quiet. Okay, now you can see my screen, and now you can see
No.
the full screen of it. Okay?
Yeah, sure. Yeah.
So I will announce you, Decio, and you can start. So welcome again. The next speaker of this morning session is Professor Decio Krause from the University of Santa Catarina. And he will speak about I cannot read here, sorry, on the attribution of quasi-cardinals in quasi-set theory. So please, Decio, go on.
Yes, thank you, Fred. Thank you, the organizer, for the kind invitation. And I'm glad to participate of this 10th conference on quantum foundations, because I have participated in some of them, and it's every time very agreeable to meet people in general, in particular people from Argentina. Thank you so much. Yes, my talk today was designed to clear some misunderstandings about a mathematical theory, which is indirectly related to quantum physics, because it is motivated by quantum physics. Then it's called quasi-set theory. Maybe some of you know it already, at least in some details. And we have some difficulties here in order to surpass some criticisms which emerge in the literature. And some of them, or most of them, are due precisely by a misunderstanding of the details of the theory. Then I prepared just a very general talk in order to try to put things in a clear way. And I submit to you, and of course, you be happy in receiving feedbacks and criticism and other criticisms and questionings and so on. Okay, quasi-set theory Q was elaborated to deal with collections we call them quasi-sets of absolutely indiscernible objects, entities, I don't know why. It's postulated that a quasi-set may have a cardinal, which expresses the quantity of elements of the collection. And we call it the quasi-cardinal of the quasi-sets. Then, third one, fact. A quasi-cardinal is taken to be a cardinal in exactly the usual sense of set theories. because they are constructed, the cardinals are constructed in the part of the theory which corresponds to the standard Zermelo-Fraenkel set theory with atoms. Then some criticisms say that there is a dependence on the notion of ordinals in the definition of a cardinal. That is, if the quasi-cardinals are cardinals, then they are ordinals. And they, in attributing a quasi-cardinal to a quasi-set, I am indirectly attributing it an ordinal, hence ordering its elements and consequently discerning them. And this would bring troubles to the original assumption of the idea that the elements would be absolutely indiscernible. Then I will try to explain how this works in the theory now. Below, we shall see some attempts to define a cardinality without relying on discerning the elements of the collection. This is just what I intend to present here. Okay, let's go on. First of all, it's interesting to see how quasi-set theories see these quantities we call quasi-sets. We imagine a quasi-set Q as a tuple composed by Qs, that is K1, K2, and so on, kappa 1, kappa 2, kappa n, which designate the kinds of things. For instance, electrons, protons, neutrons, and so on. And the lambdas expresses the cardinalities of each kind. I give an example. Sulfuric acid can be seen as HSO with the cardinals 2, 1, and 4. Then notice that we are not requiring the distinction between, say, the oxygen atoms. It's enough to have their kind expressed by the theory and their quantities. That's what quasi-set theory tries to express, without individualization of the particular elements. Also, the okay, that's the idea. Then, in saying that we needed to attribute a quasi-cardinal to a set, then I put in blue a supposed quasi-set with two indiscernible things. How to say that we have two there? Well, the usual alternative is to construct a function from the ordinal 2, that is the set of 0 and 1 in von Neumann's approach, to the quasi-set. But it's, of course, we cannot define such a function because you cannot distinguish between the elements of the quasi-set. Then there is a certain trick here. Then my option is to show that we are not doing that. We are not associating to the quasi-set the ordinal 2, but the natural number 2 taken from Peano's arithmetics. That is, 2 is seen as the successor of 0. And of course, this is not a set. Which is a set is the corresponding set in the model of Peano arithmetics, which exists in set theory. But we do not confound the map with the territory, of course. Then that is the elements in the Peano arithmetics, in the formal system, with the elements in its model, or standard model, so to say. Then that's the trick. The finite, at least for finite cardinals, which is apparently enough for doing physics or present-day physics, the finite quasi-cardinals are taken from Peano arithmetic, hence they are not sets. And please do not confound these natural numbers with the finite ordinals of the model of PA there is in the theory, or also called the Peano systems or Peano algebras. Then that's the idea, to take the cardinal from arithmetics. But some people need a careful explanation. Then this is an attempt to explain the details what is going on. The mapping which associates a natural number from Peano arithmetic to a quasi-set in the quasi-set theory, of course, needs to prove to exist. Then how do you prove that such a function exists if the theories are taken in parallel? We need to put them in just one environment. And usually we work with the model of the Peano arithmetic that exists in the theory of sets. Then we are working in set theory, and then the natural numbers are, for instance, ordinals. That's not the way I'm doing things. Are you going to do just the reverse direction? Instead of going from piano arithmetics for set theory, I'm going from set theory to piano arithmetics. That is, I take a fact, that is, the language of quasi-set theory is recursive, etc., so it can be arithmetized. We can use the techniques of arithmetization of the recursive languages. So we reverse the direction, going to piano arithmetics. Let us call Q in quotations the Gödel number of a formula which defines the quasi-set. And we fix an attribution. There is several ways to do that. And then to this Gödel number, which in general is a huge number, we associate a natural number, 5, 3, n electrons, and so on. In the way to associate this natural number to the Gödel number is not, of course, a problem of logic, but physics is a problem of physical theory. For instance, in quantum mechanics, you calculate the quantity of electrons in each orbital by solving Schrödinger's equation. Then you specify the quantity of the elements without individualization. You say that in the first orbital, we may have just 2 electrons. We're not saying that this electron, that electron, but just 2, a natural number, without attributing individualization to the electrons. Then we can see the existence of the mapping from piano arithmetics to the Gödel number for a particular number which expresses the quantity of elements inside the piano arithmetics. That's we are going to piano arithmetics in order to show that this function does exist. Of course, I have done here a remark, just that this works for definable sets because you need to define the quasi-set. But I think that every set considered in physics by hypothesis is to be definable. Okay, that's the trick. So we enlarge the quasi-set theory, show in the title, the quasi-set theory, adding piano arithmetics. That is, I have put in red the primitive symbols of quasi-set theory, and in blue the primitive symbols of the piano arithmetics, with an emphasis to a predicate K for quasi-cardinal, which will be natural numbers. Then it is standard. Next one, please, Fred. Then you see the elements, the quasi-cardinals, are taken from piano arithmetics, and they obey the standard axiomatics from piano arithmetics. This is the standard. These are precisely the first-order piano arithmetics. You can pass. Go on. Then we can use a terminology. I write in the pair Qn to mean the quasi-set with a certain quasi-cardinal n. This is just a meta-level notation. But we can rewrite some of the axioms of quasi-sets using this terminology. For instance, when 2 quasi-sets are indiscernible, they cannot be equal because I don't have identity for certain elements in the theory. This is supposed here. But I would say that 2 sulfuric acids, 2 molecules of sulfuric acid, for instance, are indiscernible. They are not exactly identical, but they are indiscernible. That's the idea, when they are indiscernible. The answer is that when they have the same quantities of elements of the same sort, of the same kind. And this is formulated as above. I think we don't need to read it with details, but just take the idea. Then it's an axiom of extensionality, but in a weaker form. Okay? Then you can go for other axioms. For instance, 2 quasi-sets having the same quasi-cardinal and being indiscernible, then this quasi-cardinal must be the same. Just structural ones. The second one is perhaps more important. If Z of Q means that Q is a set, a copy of a standard set of a standard set theory. For all elements, identity holds and so on. Then when a Q, which is a set, has a quasi-cardinal, this quasi-cardinal is precisely its cardinal in the standard sense. Then we recover the idea of the cardinals for elements which obey the standard requisites. In other axioms are just the operational one. For instance, axiom 3. If you have a quasi-set and we have a natural number, then if you have an indiscernible quasi-set, and if this quasi-set indiscernible from Q has some cardinal, quasi-cardinal, then it must be precisely the. And notice that the identity here holds for natural numbers. The other ones are also axioms for structural axioms. Axiom 4, for instance, for each quasi-set and each quasi-cardinal, for all m less or equal to n, there exists a sub-quasi-set with that quasi-cardinal. When we have 5 elements, then I can suppose the theory is consistent with the idea that we can form sub-quasi-sets, so it's 0 elements, 1 element, 3 elements, 4 elements, and 5 elements. Okay? Yeah, the other axioms are also just structural axioms, saying things which enables us to treat the quasi-cardinal as if they are how they are natural numbers, and just I will not read. I will read just the eighth one, the last one, because this is important for the idea. That is 8 for a quasi set Q and a natural number n. If Q has n as its quasi-cardinal, then the power set of Q has precisely 2 to n elements. And this is important because please at the next step. This is important because if we have, for instance, 3 elements, n equals to 3, you may reason as if you have one subset with 0 elements, 3 subsets as 1 element each, 3 subsets with 2 elements each, and 1 with the own subset with 3 elements. But the important thing is that, for instance, the 3 with just 1 element cannot be discerned from one another. They are also indiscernible by the weaker indiscernibility extensionality axiom. But you can reason this way, that you can suppose that we have 3 subsets with 1 element each without individualizing them, without counting them. Then let me read here. We can reason as if a quasi-set with 3 indiscernible elements comprises 3 sub-quasi-sets with 1 element each, which turn to be indiscernible themselves. Also, 3 sub-quasi-sets with 2 elements each in the quasi-set itself and the empty quasi-set. So 4 possibilities we have. 4 possibilities: 0 elements, 1 element, 2 elements, and 3 elements. If you regard the distinction among the discernible quasi-sets as something to be as something which can be considered. Okay. Next one, Pat. There is a concept, an important concept in the theory, which is the strong singleton of an element X. I write it as in red, relative to a quasi-set. If X is an element of a quasi-set Q, we denote that way a sub-quasi-set of Q, which has just 1 indiscernible from X. The problem is that we cannot say that this only element is X itself, because in order to assert that it is X, we need identity, and we don't have identity. Then we can reason this way because the postulates enable us to admit the existence of this strong singleton. It will enter in the discussion below. Then there is below the explanations. When you write x1, that is a quasi-set. It's important to notice that the variable x is not naming a particular element. It's a generic variable which says one element of the kind x, if you prefer, just one element without individualization. The theory enables us to deal with this kind of things. The next one, please, Fat. So you can reason this way. As Hermann Weil's Ars Combinatoria says, we have 4 visible states. Just one state with 3 elements, with 0 elements, one state with 1 element, one state with 2 elements, and one state with 3 elements without identifying which elements are in each state. Then the theory captures this idea quite well. So I put here the way of counting with this formula in brown. It precisely will give you the quantum statistics. Okay, we can leave this. Then some criticism, but for instance, a very interesting one by Benjamin Janssen. He takes the strong singleton I just defined, the quasi-set of x, which has just one element, and defines a relation x related with y if y belongs to the strong singleton. Then he says this provides identity to the x, because if y must be equal to x. This is false, because in order to say that y is precisely the element y, I need identity. And if they are, he says, look, and guesses that since y and x will belong to all the same quasi-sets of the power set of Q, this defines the identity of x. It's false, because I put here the figure. If we have 3 elements in the Q and the power set there, how can you say that 2 elements belong to the same sub-quasi-set? We cannot identify them. Then we cannot assert, as Janssen has done. This is a misunderstanding of the theory. Okay, then I needed to surpass this kind of criticism. Janssen's claim is false, for it presupposes identity at the start, and yet that x is naming some individual of Q, yet arbitrary, so that if y belongs to the strong set of x, then y should be x, and so we would have the identity of x. This is Janssen's claim. As I told above, epsilon y belonging to the strong singlet of x just means that y is indiscernible from x, and not that it is identical to x. So y belonging to the strong singlet of x does not define the identity of x. When you say that x is any atom, that's an atom, an element to which the identity, the standard notion of identity doesn't apply, and belongs to Q, the only information we have at Q that Q comprises at least one element of the kind X, but without individualization. The atom has, for instance, one oxygen, but not a specific oxygen. There are other criticisms. I think I have some time here. Other criticism, other people insist that the notion of a cardinal is strongly linked to that of identity, so that an attribution of a cardinal to a set where discerning its elements. This may be true for sets in the standard set theory, and still with reservation. Take, for instance, a permutation model in Zermelo-Fraenkel with atoms, also called by some critics. They use these arguments. For our purposes, just Fraenkel's original model is enough. You could say that once any permutation of atoms can be extended to an automorphism of the whole universe, then the atoms would be indiscernible. And I am saying that the permutation models, they say, but inside the atoms in the permutation models are indiscernible. I am saying, no, they are not. They are indiscernible inside the model, but you can leave the model and see that they are different. Okay, the next one, please. Here, they are indiscernible only from the point of view that is inside of the model. From the outside view, identity holds for all objects of the domain. This axiom is acknowledged by Frankl himself when he says, before making some atoms become indiscernible. Or look at what Frankl said. To show that the axiom of a choice is independent of other axioms, this is the reason he constructed such a model, we shall consider as belonging to a domain B the following objects. First, the null sets, and also the numerable infinite number of distinct atoms, distinct objects. They are different. Then he makes a permutation of these atoms in order they cannot be discerned, and so no choice function can be defined, and consequently the negation of the axiom of choice is true. So apparently there is no chance of being able to define the cardinals without some reference to ordinal. Apparently there is no this alternative. The so-called Scott's trick doesn't rely on the axiom of choice as the standard definitions such as von Neumann's do, but on the axiom of regularity and the notion of rank. But rank also depends, the notion of rank of a set also depends on the notion of ordinal, and so the ordinals are reintroduced by the back door. Then we need precisely to find a different alternative. Next one. And also there is another criticism. It's not a criticism of the quasi-set theory, but another attempt recalled by Janssen himself, when he says that Solvaras tries to define a definition of a cardinal independently of well-ordered rings. Then Janssen recalls that Solvaras lays down a set of plausible conditions for a notion of a cardinal in any model of ZF. But look, he's working in a model of ZF, and identity is identity inside the model or outside the model. It does not work too. Any model of ZF prescribes identity for all individuals of the universe, if not inside the model, as for instance the permutation model, but then identity holds outside the model. The most we can do is to confine ourselves within a non-rigid structures, such as Frankel's, and play the game as if certain of our objects are indiscernible. But we need to be sure that no one from the outside of the model is looking at us, for she will easily discern the objects and the like. That is, someone outside the model can see that the elements in the model which are taken to be indiscernible, and this person from the outside can see, no, they are not indiscernible, they are indiscernible. This is a theorem of a standard set theorem. No way. If you aim to provide the cardinals to collections of indiscernible objects, as chemistry and quantum physics seem to require, apparently we need to go to quasi-set theory. There is no alternative. We need to. Oh, this is all. I remember here my thanks to Elisa, who has helped me in thinking about these details with kind patience and kind friendship. Thank you, Elisa, and thank you all for listening. Okay, we have time for questions. Ferdi, you are muted. Fed, you are muted.
Está muteado.
Okay. Professor Dix has a question. Please go on.
Oi, Dennis.
Thank you, Decio, for your talk. I was wondering about this quasi-set theory. So,
yeah, I know.
So I was wondering, it isn't really needed to introduce something complicated like that, because an alternative seems to be that we speak about, well, let's say n greater than 1, n quanta in one state, like in quantum field theory. So instead of saying there are n entities which are indistinguishable and conform to rather strange logical rules, we could just very simply say it's one whole, like what you say in classical physics and also in classical logic. You have so-called mass terms, like a total quantity of, let's say, water or some other continuous substance. And there is no point in it to say, oh, there are actually n liters or other quantities inside which obey some weird rules of logic. So is it not much simpler to do without quasi sets and to say it's just one big whole? I'm interested in hearing what you have to say about that.
Yeah, of course. I know about your suspicions and criticisms, because perhaps yes, of course, it can be done from some alternatives. But look, Dennis, when you speak about quantum field theory, for instance, Fock spaces.
Yes.
When you say that you have a certain state, occupation number, the occupation number is n, then you just think about attributing n elements without individualization. But it's not true, because you need to work in some framework. And I ask you, where this Fock space is being built? The answer is within quasi-set theory, is a standard set theory. A Hilbert space is as a set. The vectors, the number operators are also operators acting on sets. Then necessarily in the underground, in the basic mathematics, where you put your Fock space, you discern the things. Even if you think that you are not discerning them in the Fock spaces. But this is just a model, a set, a non-rigid structure, if you prefer. But the structure can be extended to a rigid structure. Every structure in set theory, for instance, and Melo-Frankl, can be extended to a rigid set theory. And the universe has no other automorphisms than the trivial automorphism. Then all elements are individuals. Then it's okay, you can do things in order to do physics perfectly well without such resources, complicated resources as quasi-set theory. But if you are looking for a philosophical motivation, a foundational motivation, in order to see things working as they were indiscernible from the beginning, not making discernible by artifices, for instance, to taking equivalency relations and so on, if you assume such a kind of metaphysics, so to say, then, of course, standard set theory does not work. And the same thing for mass terms, because if you say, okay, I have a cup of water and I can attribute some quantity of molecules here, n molecules in this water without counting them. But when you represent this cup of water in a set theory, you need to constitute a set. And a set is a collection of discernible elements. Then you are just omitting that the mass terms cannot be discerned. But once they are represented as sets, they become individuals. That's the answer.
So if just to see if I understand you correctly, so on the one hand, you are willing to admit that in physics you can do without the individual elements, but the mathematical theory that applies recognize them as individuals anyway. That's what you're saying. I think about it. Thank you very much.
Yes. The other question then is just to come is the question I put to Walter before another talk, because if we have a Hausdorff topology or in the space where quantum things live, if this space, the Euclidean space for orthodox quantum mechanics, is a Hausdorff, then any two individuals are ever distinguished because they belong to distinct open balls. Then you cannot speak about indiscernible at all with such a kind of topology. This brings us another kind of problem from the foundational point of view. We needed to think about a different topology too. But this is another question. Thank you for your question. I hope you have understood me a little bit more. To the next.
Thank you very much. Yes, I certainly think I have understood you better.
Thank you. Very kind.
Thank you for the answer. Yes.
Thank you, Dennis.
Are there any other questions in the public? Because if there aren't, I would like to say something about what Dennis asked. I've been thinking about that a lot, but independently, I've been thinking about mathematics And what is the meaning of a set? That's a non-trivial question. Usually when when people teach about sets, they say, well, you have a collection of individual objects. Well, that's true. Yeah, that's the intended interpretation. So you have distinguishable in these individualizable objects of experience. It could be of thought or a bag of apples and so on. But it's tricky because in set theory, you have very huge collections that are infinitely many. And then the standard interpretation becomes blurry, but still you can still think about individuals. Anastasio says in standard set theory, you are ultimately speaking about entities, whatever they are, that are individuals and can distinguish. But if you change a little bit the actions of set theory, everything changes. So I think that we shouldn't think about the intended interpretation of quasi-set theory as collection of things like tiny particles or whatever they are that have the sole property of being indistinguishable. Why? Because you can change the axioms of quasi-set theory in such a way that even the number of elements is not defined in some occasions. So you can do that. And this is a very strong analogy to what happens with quanta. In quantum field theory, what you have are not tiny particles. I mean, particles appear as a sort of approximation, or it's also a way of speaking. It is a working approximation. You have other thing, which is the quantum field that has excitations. But it turns out that in some circumstances, this quanta can be counted and counted by one. It doesn't mean that you are speaking about individuals. It's like money bank. I mean, whatever it is. I mean, so when you deal with these new multiplicities that come, let's call them multiplicity, that come from quasi-set theory, you have a something which is somehow a collection, but not in a standard sense. So in some situations, these collections might have a well-defined number, but in some situations they might not. As it happens with photons in a coherent state of light, you cannot say that. I mean, it's odd to say that a laser beam is a bunch of photons. I wouldn't say that as a physicist. I don't know what you think about that, Dennis. So my position is that we cannot use the intended interpretation of quasi-set theory as if they were like just tiny particles that suddenly become indistinguishable. It's another thing. And it's not so strange because in physics, we are familiar with that idea. We have quanta. I mean, so the model is quanta. So is there any other question in the public or observation, remark? We still have some 3 minutes. So if there aren't,
Okay.
we can thank again
Thank
Professor
you,
Krause.
Thank you all. Thank you, Dennis. Thank you, Fed. Thank you.
Thanks,
people.
Tessie. Thanks for being here. So
Okay,
now
it's a pleasure.
yes, thanks. So we have, if Angel is there, please try to share your screen.
Hello, good morning, everybody.
Hi, how are you doing?
Can you see?
Please. Not yet. You should try to share your screen first. When you click on the green button of share screen, do you see something?
Yes.
And what do you see? Now something is happening. Perfect. Now it's perfect. Now try to put, please, full screen mode. I think it will be Control L. If you click Control L, yeah, in Adobe it works. Control L, yeah, usually works. Yeah.
Can you see the full?
Yeah, it's full, but it is somehow flat. No, but I think it's fine. I don't know the rest of us. What do you think? If I think it's good.
Yes.
Is it good?
Yes.
It is readable. Can you read it?
No,
Yes.
no, it's readable. It's perfectly, yeah. So, okay, we're in. So now we are glad to have Professor Ángel Ricardo Plastino from the University of Noroeste from CONICET from Argentina, and he will speak about facets of quantum entanglement from the perspective of Bohmian mechanics. Please, Ángel, go on.
Okay, thank you. Well, good morning, everybody. I will talk about a work we did in collaboration with Claudia Sander from University of Pretoria, South Africa, where we studied some aspects of quantum entanglement from the perspective of Bohmian mechanics. Let me briefly say something about why we should consider entanglement from the point of view of Bohmian mechanics. Well, there are a few reasons. First of all, well, as we all know, Bohmian mechanics has a considerable historical and conceptual interest. It is interesting, for instance, as an example, that Tegmark and Wheeler in the year 2000, they wrote a nice article in Scientific American celebrating the first 100 years of quantum physics. And there is a very, if you check that, there is a very nice picture of a list of significant events in the development of quantum theory, and they included as one of the significant events on the development of quantum theory in the first 100 years. They included the proposal by Bohm of his hidden variable theory. Indeed, Bohmian mechanics provided stimulating new perspectives on several fundamental aspects of quantum physics, including the measurement problem, quantum chaos, quantum cosmology, and many others. And Bohmian mechanics highlights a basic feature of quantum physics, which is that all measurement processes in quantum physics are ultimately kinematical in nature, in the sense that they are ultimately based on the observation of the position of an object. That is the position of a particle, or if you want to call it, the position of a pointer. And also, it is worth to consider entanglement within Bohmian mechanics, because after all, Bohmian mechanics is the paradigmatic hidden variable theory. Hidden variable theories are still important in many respects. First of all, they provide in a sense, the conceptual background against which a large part of research in quantum foundations is done. Actually, a large part of research in quantum foundation is devoted to efforts to rule out particular classes of hidden variable theories. And in that sense, Bohmian mechanics is powerful, because Bohmian mechanics is a hidden theory that is completely equivalent, at least in the non-relativistic regime, completely equivalent to standard mechanics, so it cannot be ruled out. Also, Bohmian mechanics is the simplest and most straightforward hidden variable theory, and still constitutes the most studied, the most developed, and in many respects, the most encompassing hidden variable theory, because it's not a hidden variable model that was constructed in order to study one particular restricted scenario, like, for instance, Perez magic square, but it's a hidden variable theory that includes a reasonably wide family of physical phenomena. Essentially, all non-relativistic phenomena can be are included by Bohmian mechanics. Well, in spite of all these features, it is surprising that relatively little attention has been paid to the quantitative study of entanglement within Bohmian mechanics, and that's what we have tried to do. Let's first remind us some very basic aspects of Bohmian mechanics. Well, you know, in Bohmian mechanics, particles are governed by a classical-like equation of motion, and the Bohmian particle has a definite position and velocity at each time, and the velocity field is given by the wave function according to this equation that is shown in the slide. But the precise position of the particle is not known. It is described by a probability density, which is given by the square modulus of the wave function, and which obeys a continuity equation. What we want to do is to study entanglement between two Bohmian particles. We are going to consider two particles described by a pure state. For simplicity, we consider two particles moving in one-dimensional space, but all the results can immediately be extended to multiple dimensions. And well, from the point of sorry.
Perhaps the sound is gone.
Can you hear me?
Now, yes, I can hear you.
Okay, so as I said, we want to study the entanglement between two Bohmian particles described by this pure state. For simplicity, we consider one spatial dimension, but everything can be extended to n dimensions. From the point of view of standard quantum mechanics, we can measure quantitatively the amount of entanglement of this state by considering the degree of mixedness of the density matrix associated with one of the particles. And as a measure of the degree of mixedness, we can consider the linear entropy of the density matrix of one of the particles. In terms of the wave function, this linear entropy, which is the measure we are going to use, can be written in this as this four-dimensional multiple integral. And now, following the Bohmian approach, we can express the joint wave function describing the two particles in the polar fashion, where this function R is equal to the modulus square of the wave function, and well, alpha is the phase of the wave function. And what we are going to do is to decompose the entanglement between the two particles in two parts that can be interpreted in a classical-like way in terms of the trajectories and the velocity field of describing these two Bohmian particles. So first, we are going to consider what we call the two components of the entanglement, we are going to call them configuration entanglement and phase entanglement. Configuration entanglement will describe the classical-like correlations in the associated with this function R of x1, x2, which describes the probability density associated with the two Bohmian particles. On the other hand, we are going to have another component of entanglement, which we call phase entanglement, which will describe the non-separability of the Bohmian velocity field. So for this simple system of two particles that we are considering, the equation of motion of the two Bohmian particles are those that are shown in the slide. And which in general are going to be a set of two coupled nonlinear differential equations. In the particular case, that is, in general, when the joint phase alpha of x1 or x2 cannot be additively separated as a phase f alpha 1 of x1 plus a phase alpha 2 of x2, when that cannot be done, then the two equations of motion are going to be coupled, and the Bohmian velocity field is not separable. On the other hand, when the phase can be additively decomposed in that way, then the Bohmian velocity field becomes separable, and the equation of motion describing the two Bohmian particles are independent of each other. So now we consider separately the two contributions to the entanglement of these two Bohmian particles. On the first we consider this entanglement of configuration, what we call configuration entanglement. This measure EC, which describes, is written as you see as an expression dependent only on the Bohmian density of describing the two particles, the Bohmian probability density R of x1, x2, and it is expressed as that integral. And this basically measures the classical-like correlations associated with the classical-like probability density describing the two particles. It can be shown after some algebra that this measure is bounded between 0 and 1, where the lower bound EC equal to 0 is achieved only in the case of that the joint probability density describing the two Bohmian particles is factorizable. That is, the case EC equal to 0 corresponds to no classical correlations between the two particles as described by the classical-like Bohmian probability density. On the other hand, we have this other expression, which we call phase entanglement, EP, which depends on the phase alpha and describes the non-separability of the Bohmian velocity field. It can be proved that this one is also bound between 0 and 1. EP is also larger or equal to 0 and smaller or equal to 1. And it can be shown also that the lower bound, EP equal to 0, is achieved only in the case that the phase is additively decomposable and the Bohmian velocity field consequently is separable. So then we have these two entanglement indicators, EC and EP. EC describes, I repeat, classical-like correlations in the Bohmian probability density, and EP describes the non-separability of the Bohmian velocity field. Now, the sum of these two quantities, EC plus EP, it can be shown that is equal to the entanglement in the standard sense as measured by the linear entropy of the reduced density matrix. So as a consequence, we see that the sum is also bound between 0 and 1. So each one of these two indicators individually is bound between 0 and 1, and the sum is also bound between 0 and 1. This means that that both indicators cannot achieve their maximum, their upper bound simultaneously. In other words, if you have a state with large configuration entanglement, it must have a low value of a small value of phase entanglement, and vice versa. Well, it's easy to see also that for non-interacting and non-entangled systems, the two indicators are individually conserved. That is, the time derivative of EC is equal to 0, and the time derivative of EP is also equal to 0. But for non-interacting but entangled systems, that is, two systems that are not interacting but are in an entangled state, then the sum of the two is conserved. That is, the derivative of EC plus EP with respect to time is equal to 0. But in general, the time derivative of each one individually is not 0. That is, the two evolve in time, but always keeping the sum constant. And it's also possible to show that if EP is equal to 0, then necessarily the derivative of EC with respect to time is equal to 0. That is, at each time where the phase entanglement vanishes, then the instantaneous time derivative of the configuration entanglement also vanishes. Well, as an illustration of how these two indicators evolve, we are going to consider a nonlinear Schrödinger equation, which is closely related to the one proposed by Nassar and Miret Artes in this article in 2013. These authors proposed this nonlinear equation as a model for the process of continuous measurement of the position of a quantum particle, including dissipation effects. The equation has the form shown in the slide, where H is the standard Hamiltonian of a particle moving in the potential Vx, and WC and WF are two non-linear contributions to the Schrödinger equation involving logarithmic non-linearities, as shown in the equations. Well, we are going to consider a similar nonlinear Schrödinger equation, but considering only the dissipation term described by this nonlinear logarithmic contribution WF. This Schrödinger equation describes them two non-interacting particles moving under the effect of a joint harmonic confining potential, and with this nonlinear term describing dissipation. Actually friction. And okay, as I mentioned before, we express the wave equation in the polar form. We compute this nonlinear contribution as shown there, and we introduce an ansatz for the time-dependent wave function, depending on some of these coefficients lambda 0 to lambda 5, which are time-dependent. And if we introduce this ansatz in that Schrödinger equation, then the Schrödinger equation, time-dependent Schrödinger equation, is equivalent to a set of or the coupled nonlinear ordinary differential equations describing the evolution of the coefficients lambda. The lambda coefficients are complex numbers in general, so we have to consider the real and the imaginary parts. In the particular case of where the two particles are free, there is no confining potential and no friction, the configuration and phase entanglement evolve as shown in these two figures. Of course, the sum is kept constant, but you see that each one evolves in time as shown there. And if we include the effect of friction, then the to entanglement, the configuration and the phase contribution oscillate, but the sum now is not constant and it decays due to the effect of friction of the dissipation. These two contributions to the entanglement of the two Bohmian particles, as I described before, do not refer directly to properties of individual Bohmian trajectories. Rather, they describe global features of the Bohmian probability density and of the Bohmian velocity field. There are, however, some connections linking an entanglement within the Bohmian context with features of particular individual orbits. And this aspect of Bohmian dynamics has started to be studied systematically only very recently. As an example, I mentioned these papers by Semos and Kontopoulos from Athens, where they show that the entanglement between two Bohmian particles is closely related to some features of the individual trajectories, in particular the chaos and velocity properties of individual Bohmian trajectories. Well, our aim is to explore some applications of these indicators of entanglement. In particular, one thing that we consider may be of some interest is that these indicators of entanglement, which are associated with classical-like features of the Bohmian dynamics, that is with the classical correlations of the Bohmian density distribution and the non-separability of the Bohmian velocity field. These two entanglement indicators can be evaluated and studied in cases where the standard cannot be computed in the standard way, which happens with some extensions of Bohmian dynamics that had been advanced recently. As an example, we can mention Valentini's work on an extension of the Bohmian model called quantum non-equilibrium. Here I provide one reference in this respect. This extension of the Bohmian model is related to a feature of the Bohmian model that has been discussed a lot in the literature from the very beginning, which is that the fact that in the Bohmian model, one assumes that the probability density describing the Bohmian particles is equal to the square modulus of the wave. That probability density satisfies the continuity equation associated with the Bohmian velocity field. But in principle, one can Hello, can you hear me?
Sometimes the mic chops off your mic somehow, perhaps due to the connectivity. But yeah, perhaps the last you said it was cut. You can say it again. Yeah, the last thing you said.
Because yeah, right now it appeared a sign saying that there was a connectivity problem. But now
yes. Yeah. At some points it cut off, but just a little bit. But now the last part was yeah. You can repeat perhaps
yes,
the
sure.
last. I was saying
that I was saying that these entanglement indicators can be evaluated in cases where the standard quantum entanglement cannot be computed in the standard way. And this happens with some extensions of the Bohmian model that have been proposed recently. And as an example, we have Valentini's quantum non-equilibrium extension of the Bohmian model. This quantum non-equilibrium extension considers a problem that refers to a problem with the Bohmian model that has been bothering people from the very beginning, since Bohm introduced it in the 50s, which is that Bohm needs to assume that the probability density of the Bohmian particles is equal to the square modulus of the wave. And we can let it evolve according to the Bohmian velocity field. And so it was, there is in the literature a lot of discussion trying to justify why we have to use the particular probability density used by Bohm and not an arbitrary probability density and that evolves according to the Bohmian velocity field. And if we consider this more general setting where we allow other probability densities, then we cannot compute the standard quantum mechanical entanglement. But these two indicators that we introduce here can be computed, and it's possible to study how they, for instance, how they evolve in time or their main properties. And another thing that we would like to maybe to consider in the future is to apply this kind of indicators directly to purely classical problems. Like the most straightforward application would be to classical gradient dynamical systems with time-dependent potentials, which appear in many applications in physics and other fields like biology. But it also might be applied also to classical Hamiltonian systems. And a question that I asked some friends from statistics or probability theory, is that what if this quantity that we introduce as this measure EC is if it is we would like to know if it has been applied somewhere within classical statistics. We couldn't find any place where they use that particular structure to quantify classical correlations. Maybe someone in the audience can help us, and if they know that this kind of measure has been applied classically somewhere. Well, for more details, you can see this article. And finally, I would like to say congratulations to the organizers for the 10 years of the Quantum Foundations Conference. That's it.
Okay. Thanks, Angel. Thanks for being here and this wonderful talk about this great interpretation of quantum mechanics. And now we open the mic for questions. If someone has a question, please go on. Please, Sebastian, go on.
Hello.
Hello, Angel. Thank you for your talk, and thank you for expanding the frontiers of Bohmian mechanics. I have a question. Is in the beginning of your talk, you say that you will work with pure states.
Yes,
do you
right.
know if the Bohmian mechanics formalism allow us to work with a mixture of states? Because I know that they use the wave function, so and not the
density
state
methods.
Yes. So do you know if it's possible to work with these states or not?
Your question is if it would be possible to adapt this approach to mixed states?
Yes.
Yeah, that's an interesting point. I think it would be possible to adapt it to mixed states, but I'm not sure exactly how to, but yeah, I think it's possible to. But you are absolutely right. Most people working with Bohmian mechanics consider only pure states, not mixed states. But I think it's possible, yes.
Okay.
But well, maybe we can discuss that point sometime in the future.
There is another question from Dennis.
Yes, Professor Dix, please go on.
Thank you for your talk. I was a bit surprised to see that if you use the measure you proposed, that there is a kind of complementarity between the correlations in the positions and the correlations in the velocities because of this sum being
Right.
constant. So if one goes down, the other goes up.
Yes.
And so could you give some kind of intuitive idea of what that means? Because it surprises me, because I would say if things are very much correlated in position, then their velocity should also be correlated. But if this stays on, if it remains constant in time, and so I'm a bit surprised. So if it would be helpful if you could give me some kind of intuitive idea of what's behind this.
Yeah, that's also a good point. Yeah, of course, the sum stays constant only for non-interacting systems. I mean, if the system interact, then the sum, which is equal to the standard quantum mechanical entanglement, then it will evolve. But if the two systems are not interacting, yeah, you're right. The sum is constant, but each one is not constant individually. I mean, the system goes from phase entanglement to configuration entanglement back and forth. The thing is that, actually, both measures cannot be achieve high values simultaneously because the sum is bounded from above by one. That can be proved mathematically. But an intuitive picture, what I would say is that if you assume you have a velocity field describing these two particles. On the one hand, then you have the classical correlation of the probability density, and on the other hand, you have this measure that measures the non-separability of the velocity field. But this second contribution, which we call EP, does not depend on the velocity field only. It actually is a combination, depends on the velocity field and on the probability density, because you can interpret it as a measure of the non-separability of the velocity field, but where different points in configuration space do not have the same weight. In a sense, they are weighted according to how populated they are by the density.
Okay, thank you.
Okay, are there any other questions? If there are not, we thank again Angel for his talk. And today we come back at 2 o'clock. Remember that all times displayed in the program are Argentina time. Yes, Martin. Okay, so see you again all at 2 o'clock.
Stop.